So, hello everyone. Welcome to the live section of this course from Foundation of Classical Electrodynamics. So, I'm Gitanjali. I'm a PMRF scholar from IIT Delhi. And as I said before, in each weekly live session on Friday, we'll go through the lecture content and I will try to solve a few assignment problem or other than the assignment problem, I will try to solve any uh, problems that is related to the concept that has been taught during this week. So let us get started. In this week, we mostly see what are the definition of electrostatic potential and electrostatic energy, and how we can get it from what is the definition of electrostatic field and what are the condition of electrostatic field and how when we say a field is electrostatic, then we can express that field in terms of gradient of some scalar, which is the electrostatic potential for our case. And after that, we saw what are the how we can find out the electrostatic potential of any type of charge configuration. It can be a discrete charge configuration, which will have a discrete amount of charges which are distributed randomly, or it can have a continuous charge distribution, which can have a line charge or surface charge or the volume charge density. So based on this concept, we will see a few problems and we'll try to solve. So before that, let me know whether my voice and whether the screen, the solution screen is visible to everyone or not, because last time there was a technical error from my side. So let me see whether my voice or screen is visible. If not, let me know uh, beforehand, then we'll start. Okay, if it is visible and audible, let us start our session. So this is the problem that we haven't solved in last. This is one of the problem that we haven't solved in the last live session. So let us solve it first, then we'll see problems related to week 5. So this problem is to find out the electric field at the center of a circular ring. So let me read out the question for you. The question says, there is a upper semicircle of a ring which have line charge density of lambda, and the other semicircle has line charge density of minus lambda. So the problem asks to find out what is the electric field at the center of the circle. So let me draw it first. So we have a circle like this, and in the first half of the semicircle, we have plus lambda, and in the second half, we have minus lambda. And the question asks to find out the electric field at the center. So the solution or the procedure is the same. We need to take a small area element. Then we need to find out what is the small field that will be produced by it. Then we'll integrate it over the whole circle to find out the total electric field at the center. So for this, let us say at an angle theta, we have a small length element which will have charge dq. and the radius is r. Now, because of this small element, the field will be in this direction, right? And if you see, there is a symmetric area element in the opposite side of this circle. So for this one also, which is also, let us say, tan angle theta, and this is d theta. For this length element, we'll also have a electric field which is also pointing in the same direction, because this is minus lambda and this one is plus lambda. So both are filled electric field in the same direction. So that is why they will add up to find out the total electric field. So for the upper semicircle, the field will be K dq by capital R square and RK. dq will be lambda and R d theta, right? RK divided by R. So, 1 R will cancel. So we have K lambda d theta over R RK. So this is only one part of this circle. For the next half, this will have the same magnitude, but direction is also same. So that is why we'll add up the two small electric field. Okay. Now we'll see whether there is a symmetry in the electric field or not. So if you see, let me think. For this direction, the electric field can have this direction or in the perpendicular direction. But this direction, it will cancel with the field due to the opposite direction. So that is why we will have only electric field in the perpendicular direction. Okay. So now the arc will simply be minus J2. So we have electric field, which is 2 dV sin theta minus J2. So just put the value of dV. We have sin theta d theta minus Jk. And because we have already taken 2 times of electric field, that is, we have considered this element, also this element. So the theta integration will be from 0 to pi. Instead of 0 to 2 pi, we'll take 0 to pi. And this is easy to find out. This will give cos theta 0 to pi. So we'll have minus lambda by pi epsilon r. Okay. So I hope this question, the solution is clear to you. So this is all about week 4. We'll start solving problems that is related to this week, which is week 5. So the first question, it's a easier one. You just need to find out what is the flux through a surface. So I would suggest calculate the flux and let me know the answer. The question is, there is a field, which is A, is y I cap plus z j cap plus x k cap. So the problem is to find out the flux through a surface which has y equal to 1 and x is between 0 to 1 and z value is between 0 to 2. There are four options. First option is 1, second is 2, and third option is 3, and the last option is 4. Anyone? So here you just need to find out what is the expression for the surface. Option B. Yes, this is correct. Okay, so then you know how to calculate it. So let me go through the solution briefly. So because y is a constant, the area element will be dx, dz, jk. So flux will be A ds, which is A dx dy jk, and the component for jk is z jk. So we have z dx dy. Sorry, and this is dz. So this will give z square by 2 from 0 to 2 and x from 0 to 1. So it will give a value of 2. Option B. Okay, so let us move to our next problem. So in next problem, we have a long cylinder which has charge density. It's given rho is Ks. S is the distance from the axis of the cylinder and K is the constant. And the question asks to find out what is the electric field inside the cylinder. So for this, we can use the Gauss law because if you use the Gauss law, it's easy to find out what is the electric field expression either in inside or outside or at the surface of the cylinder. But please remember, you can only use the Gauss law. Gauss law is always valid, it's no doubt, but uh, to find out the electric field using Gauss law, you need to check whether the system has a symmetry or not. Because only when the system has symmetry, you can take the electric field out of the integral. Then you can easily find out what is the electric field for at the different region of a either cylinder or a sphere or a hemisphere or whatever the system is asking about. So Whenever you are seeing a symmetry, you can use the Gauss law to find out the electric field in short term. If not, if there is no symmetry, then you have to follow the usual procedure. Like you have to take a small area element or small length element or a small volume element. Then you have to find out the small electric field, then integrate it to find out the electric field at the particular reason the question is asking about. So for this, it's a cylinder, it's a long cylinder. So and the charge distribution is symmetric, which is rho is ks. So the system is symmetric charge distribution. So we can make use of the Gauss law. So Gaussian surface will be symmetric to the system that we are considering. So for a cylinder, we can take a cylinder as a Gaussian surface. So let us say this length is L and the radius is S. And electric field is in this direction. So we can use E dot dA is Q enclosed by epsilon. So because the electric field is in this direction, only this area element will contribute to the total flux. And the area of this curved surface will be 2 pi rs, right? This I think all of you already know, but how to find out the area element. If not, let me know. So E is 2 pi SL and Q enclosed will be, so it's a volume charge, so it will be rho dV by epsilon. So rho is Ks. dV for a cylindrical coordinate, you can take this will be S d phi ds dz. Triple integration epsilon 1. So we have K square ds. S will be from, for inside, it will start from 0 to small some radius s, and d phi it will be from 0 to 2 pi. Dz will be minus L by 2 to L by 2. So this will give K is K by 3 to pi L by 7. And in the left hand side, we have E 2 pi SL. So that means we have electric field. This 2 pi will cancel, L will cancel, S K S square by 3 epsilon naught SK. So the answer will be option B. Okay, so let us move to our next problem. So it's a easier one. Calculate it and let me know the answer. So let me read the question first. So there is a potential which is given as phi is x minus y plus xy plus 2z. So the question asks to find out electric field at 1, 2, and 3. What is the electric field? Option A is 3xk plus 2zk. Option B is minus 3xk minus 2zk. Option C is 3xk minus 2zk. And D is minus 3xk plus 2zk. So you just need to use electric field is minus of gradient of the scalar potential. Minus 3 I cube minus z cube minus 2 kk. But there is no option like this. Only x cap and k cap is given. So let me show you the step and check whether any of your step is following the same steps or whether you are missing anything. Okay. So for Cartesian coordinate, we can take delta as I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. And phi is x minus y plus xy plus 2z. So we have minus I cap dou by dou x of x will give 1, y will give 0, and xy will give plus y, and 2z will give 0. So this is 1 plus y, then minus j cap dou by dou f minus y will give 1, xy will give plus x minus k cap dou by dou z of 2z will give 2. So we have 1 plus y I cap minus j x minus 1 j cap minus 2k. And the point is given, xyz coordinate is given, it is 1, 2, and 3. So just put the value of xyz, you will get this is y is 2, so minus 3 I cap. X is 1, so this is 0, and this is 2k. So that means this is minus 3x cap minus 2z cap. So the answer will be option B. Okay. So whenever this type of problem is given, first differentiate the potential. Don't put the value of x, y, z in the function. First, calculate the potential, calculate the general expression of electric field. Then, after getting the expression, you can put the final values, the final coordinates you are looking for to find out the electric field expression at that point. Okay. So, I hope this problem is clear. Let us move to our next problem. Question says there is an electrostatic potential, which is phi x, y, z is a minus b x square plus y square minus c log x square plus y square. A, B, C are constant, and you need to find out what is the okay. So Dinakar, is it clear? Is it clear to you now? Maybe you have swapped the coordinates to find out the final values. Okay. So we have the potential and we need to find out what is the volume charge density. So this is easy. You can recall the Laplacian equation. So this is not exactly Laplacian, it is Poisson's equation to be exact. So del square B is, yes, del square B is minus rho by epsilon. When rho is 0, it's a Laplacian equation. And when it is not, then we say it is a generalized equation, which is Poisson's equation. So these are directly related. You just need to find out what is the del square of V. Del square is the Laplacian operator, and in Cartesian, it's easy to find out because the expressions are easy. So del square V or phi, you can take whichever you want, dou x square. So this will give from this minus 2b minus c dou by dou x of 2x x square plus y square. Similarly, dou square b by dou y square, double derivative, it will give minus 2b minus c dou by dou y of log s will give 2y x square plus y square. So that means rho is minus epsilon naught dou square b by dou x square plus dou square b by dou y square. Just put the values here. You will get this will be epsilon naught minus 4b minus c y square minus x square plus y square whole square plus x square minus y square. So this will cancel. So that is why we will have the charge density, which is 4b7. So the answer will be 4b epsilon. Let us move to our next problem. So it's a problem from grade 5. There is two spheres which have each of radius r, and one of this sphere carrying uniform volume charge density plus rho, and other one is carrying minus rho. And they are placed so that they partially overlap with each other. If you see this figure, they are partially overlapping with each other. This one, it is plus rho, next one is minus. So that the field in the region of overlap is a constant. So whenever you have a situation like this, in the overlapping region, we'll see that the electric field is independent of the uh, distance at which we are trying to calculate the electric field. So it is independent of R. Okay. So let us do this. So the solutions is easy. First, you need to use the Gauss law to find out the electric field due to a uniformly charged solid sphere. Then you can use that to find out the field at the overlapping region. So for field inside, so for S less than R, so if you see, this is the sphere and this is symmetric charge distribution. So that means we can use the Gauss law, and the Gaussian surface will be a sphere at a radius S. The electric field will be in the radial direction. So if you use the integral form of Gauss law, dc dot ds is q enclosed by epsilon naught, and let us see first q. The Q enclosed will be rho dV. Rho is uniformly distributed, so we can take out from the integral, and this is dV. And for sphere, you know, dV has expression of r square sine theta, d theta, d phi, dr. Don't forget this dr. And the integration limit will be from 0 to r for r and from 0 to 2 pi for phi and from 0 to pi for theta. So this will give rho and the volume of a sphere, which is 4 by 3 pi r. But this is for the whole volume of this sphere. For a sphere inside this solid sphere, the Q enclosed will be from 0 to S. So we have Q enclosed is rho 4 by 3 pi S cube. So now E, E will be in the escape direction and dA will be in the R direction. The area vector is S d theta S sin theta d theta, sorry, sin theta d phi escape, which is rho by epsilon naught 4 by 3 pi S. E is uniform, we can take out, and integration of this will be 4 pi S. So this will cancel. So for sphere, we have the electric field inside is rho by 3 epsilon naught S. Okay. Similarly, if the charge density is minus, we'll have electric field is in the opposite direction. So it is rho square by 3 epsilon. So now we know the electric field. So let us see the overlapping region. This is A, B. Let us say we are trying to find the field at the point P here. So we're trying to find it here due to plus rho and minus rho. And this one is given D. From this figure, you can say AB plus BP is AP, right? So that means AB is AP minus BP. AB is given, which it is D, AP minus BP. And the electric field at the point P, it will be the superposition of the electric field due to plus rho and minus. And because the point P is inside, we are using the expression of field which is inside the sphere. So EP will be E at point P due to plus rho and E at point P due to minus. So this is rho and the distance is AP by 3 epsilon naught plus, so this will be minus rho and this distance is BP by 3 epsilon. So you can see here we are finding an expression of AP minus BP, which is nothing but the distance between the center, which will always remain constant. So that is why the electric field of the overlapping region for these two spheres is a constant. Okay. So is this problem clear to you? Whenever this kind of problem is given, then you can always use the superposition principle to find out the electric field. We'll see the next problem is it's a slightly different one. We'll see how we can use superposition principle to find out the electric field. Go through the question once. Let me first read out the question. So there is a large conducting plate with a surface charge density sigma. It has a circular hole of radius r cut in it. So find out the electric field at a point P lying on the axis of the hole and at a distance r from the hole. I think it's better if I draw the diagram. So there is a infinity large conducting plate. You can recall the electric field due to large conducting plate is sigma by 2 epsilon naught. This we have derived it using the Gauss law. But inside this large conducting plate, we have a hole here, circular hole. And the question asks to find out the field at point, which is on the axis of this hole and at a distance r. This is an infinity large conducting plate. To solve this, what you can use? So you can say this plate, we can make it by taking a large conducting plate of charge density sigma, which is charged all over it. So there is no circular hole here. Plus, there is a circular plate, which is charge density minus sigma. So that when you superimpose these two, then in this circular hole, because of plus sigma will cancel with minus sigma, then there will be no charge. So we'll see a hollow circle which is no charge. Okay. So this situation you can imagine like a superposition of two systems. One is large conducting plate with no hole in it, plus a circular plate which is charged minus sigma. Okay. So now it's easy to find out the electric field. So electric field is due to flux sigma, which is the last conducting plate, plus electric field due to minus sigma, which is a circular plate of charge minus. Let us say this is EA. Is E. For EA, what was the procedure to find out the electric field? So because the charge distribution is symmetric, we can use Gauss law. So the Gaussian surface will be a rectangular pillbox in both sides of this large conducting plate. And the electric field is in this direction. So let us say this area element is A. Similarly, because of this large conducting plate, we'll have electric field in this direction also because it is radially outward. So for the back surface, we'll have electric field pointing outward. So that is why when we take the Gauss law, P dot ds is Q enclosed by epsilon. So E and A in the same direction, you can take out the electric field. And ds will be 2. One from upside E dot A and one from bottom side A. Okay, so you have already solved it, I think. Let me see whether your answer is correct or not. Yes, good. Your answer is correct. Okay, then let me solve it. So Q enclosed will be sigma A by epsilon naught. So E will be sigma by 2 epsilon. This is for the last conducting plate. And for the circular one, even if you don't know the final expression of electric field, you can easily calculate it. So it's always a good practice if you know how to calculate if you know how to calculate the field instead of uh, recalling the final expression, because it's hard to recall every solution for every uh, so we have a circular plate of minus sigma and the procedure is same. You can take the distance r. We have a small area and this is y. This distance is r. So r, if you see, r will be y minus r. So y j cap minus r r. So the small area element will be dB, which is beta dq r k by r square. Beta is 1 by 4 pi epsilon naught. So I'm not writing that. So you can y j cap minus r r cap by r. This won't contribute to the integration because it has a radial symmetry. So whatever the field is in this direction, they will cancel the field due to this direction. So total field will add up in j direction. So we have beta dq y jk y rq will be y square plus r square. Now I think everyone know how to find out the integration. So the q will be sigma 2 pi r dr y jk y square plus r square. So EB is integration of dB. So pi beta sigma y so because the sigma is negative, so there is a negative sign here. And this integration we already know. This will give 1 by r. 2 pi beta sigma y minus 1 by y square plus r square from 0 to 1. So we have 2 pi beta sigma y 1 by y minus 1 by square root y square plus r square. Y is nothing but the distance is given, it is r. EB, now we have sigma by 2 epsilon naught R by square root R square plus R square minus R. So I have taken Y inside and calculate the total. So we know EB now. So EP will be EA plus EB. Sigma by 2 epsilon naught JK plus so answer will be sigma by 2 epsilon naught R by square root R square. Okay. So this is how you can use the superposition principle to find out the electric field. Okay, this problem is over now. Let us move to our next problem. Please calculate the solution first, then I will go to the question. Okay, first let me read out the question. There is an consider a hollow charge cell of inner radius A, outer radius B. The volume charge density it is given. Rho R is K by R square. K is a constant. In the region A, R, B. So you need to find out the electric field at a distance R greater than A. So you have a concentric field. Inner radius is A, outer radius is B. And in between, we have distributed the volume charge rho, which is K by R square. You can see here it says symmetric uh, charge distribution. So that means just use the Gauss law to find out the answer. Okay, if it is taking time, so let me go through the solution. So for inside, for r greater than a, we can take a Gaussian surface, which will be a sphere, and for between the two concentric sphere, we have E dot ds is Q enclosed by epsilon naught. So for sphere, we can get this is E 4 pi r square, and Q enclosed will be rho dV, and rho is K by r square. And when theta and phi are in the whole limit of a sphere, like when theta is from 0 to pi, and when pi is from 0 to 2 pi, you can take dV as 4 pi r square dr. Instead of writing r square sine theta d theta d phi dr, you can write 4 pi r square d. So this 4 pi will cancel, r square will cancel. 1 by epsilon naught k d. And the limit for r is from, because it is q enclosed, so q will be non-zero when r is a, and for inside it will be to up to a point of distance r. Or you can take, for our case, this is. So now electric field is, for inside, we have 1 by epsilon naught r square k r minus a r k. So this is also the answer. This is for the inside one, and for the outside one is, okay, if you're getting this, then you are following the correct steps. For inside one, for outside one, it is easy because we know the electric field inside, and the charge q is non-zero up to a point of radius r equal to b. So the limit for integration here is from a to b. That is why the electric field will be k epsilon naught r square b minus a r k. So this is for r greater than b. So the option will be C. Okay. Let us move to our next problem. So there is a line charge density which is surrounded by a cylindrical cell with inner radius A and outer radius B. And the charge density is rho is K S square. Find the electric field in the region S less than A between AB and when S is greater than B. So you can see all these problems are based on Gauss law. And when you use Gauss law, it's easy to find out the electric field and it is easy to get it. So there is a linear line charge density lambda, and you have is surrounded by two cylinders, inner radius A and outer radius is B. Rho is given is K is square. Cylindrical cell, so it is filled inside this region. So for cylinder, the ds will be 2 pi SL. Because electric field is in this direction, so it will take the area vector of the curved surface. So we have the ds will be 2 pi SL, which is Q enclosed by epsilon. Okay, so now we will see the different reason. For S less than A, what is the charge density that is? For S less than A, we have only line charge density of lambda. You can see here line charge density of lambda. So that is why we'll only consider Q enclosed as lambda L. So then U 2 pi SL will be lambda L by epsilon naught. So electric field will be lambda by 2 pi epsilon naught S square. This is for the inside. Now we'll see the in between region when S is lying between A to B. So for this situation, we have both the line charge density as well as the column charge density. You can see here the space between this cylinder is filled with column charge density rho is K. There is a line charge density lambda here. Let us say we are considering at a distance S. The Gaussian surface is same. Okay, so first let us see Q enclosed, which is lambda L plus rho dV. And rho you can see it is K S square. And dV for the cylinder, we can write it as S ds d phi dz. S is from 0 to S. Z is from minus L by 2 to L by 2. And phi is from 0 to 2. So this will give lambda L plus Z will give L. So K L 2 pi is 4 pi 4. So we have lambda L K pi is 4 minus root of 4 by 2. So electric field 2 pi is L lambda L K L pi. So the final expression is so lambda plus K pi is to 4 minus A4 by 4 pi epsilon naught S. Okay. Okay, this is for the in between. When B S is greater than B, then it's easy because we already have the expression for the inside. For outside, only the limits will differ. So S will be from A to B. So that is why electric field will be 2 lambda plus K pi B to the 4 minus B to the 4 divided by 4 pi epsilon naught S square. So is this clear? The solutions? Let us go through the next problem. It's based on finding the electrostatic energy of the system. So calculate it and let me know the answer. Okay. First, let me read out. There are 3 point charges, minus 1 nanocoulomb, 4 nanocoulomb, 3 nanocoulomb. These are placed at one is at the origin, one is at the z-axis, one is at the x-axis. And the total electrostatic energy of the system is the distance is given in the meter. There are 4 options. Calculate it and let me know the answer. Option A. Let me see. Okay, let us calculate this. I think option A is the correct one. So work done or the electrostatic potential energy. If you recall, it's given as half of summation of I naught equal to say Qi Qj 4 pi epsilon naught mod Rc minus mod F. This you can take it as Q1 Q2 4 pi epsilon naught R2 minus R1. This is one term. Other term will be Q2 Q1. This will add up and we'll get 2 times of Q1 Q2. So this will become 4 pi epsilon. Previously we have 8 pi epsilon. Now it is 4 pi epsilon. And other pair we have Q2 Q3 4 pi epsilon naught R3 minus R2 plus Q3 Q1 4 pi epsilon naught R1 minus R1, R2, R3 are given. One is at the origin, one is at Z, one is at X-axis. So just put the values. Q1 is minus 1 nanocoulomb, Q2 is 4 nanocoulomb. So we'll get minus 4 MC square 4 pi epsilon naught. R2 minus R1 will give 1 plus Q2, Q3 will give 12 nanocoulomb square 4 pi epsilon naught. R3 minus R2 is 1 is x cap, 1 is j cap. The mod will give root 2 plus Q3 Q1 will give minus 3 nanocoulomb square 4 pi epsilon naught. This is 1. So 4 pi epsilon is 9 into 10 to 1 9. 1 by 4 pi epsilon naught. And you get 12 by root 2 minus 7. Nanocoulomb square will be minus 18 joule. So that means we have 9, 6 root 2 minus 7 nanojoule. Okay. Okay, so you are correct then. The answer is option A. Okay, so let us move to our next problem. Next problem, it's a easier one. First, I think for first case, you can easily guess what will be the potential at the point P due to two discrete charges plus Q and plus Q. These are separated by a distance T. So this is the one of the way of finding the electric field when you know the potential. So because electric field is a vector quantity, so that is why we need to take care of the unit vector that we are considering whenever we are doing the integration. But for potential, it's a scalar one. So that is why uh, you can also follow the this process. Like you can calculate the electric field by using the same conventional method by taking a small area element, then integrate it to find out the electric field. The second method is to use the Gauss law to find out the electric field for a symmetric charge distribution. And the third one is if you know the potential, then you can easily calculate the electric field by taking the gradient of this. And because the potential is easy to calculate, then it's always a easier steps to calculate the field from the potential. So this is also one of the way. Okay. So for the first charge configuration, we have plus q separated by distance d, and we need to calculate the potential and the field at a point P, which is at a distance z from the midpoint of this line joining the two charges. So I think you can easily guess this will be for plus q and minus q. This will be beta q by mod r. R is the this distance, the charge and the observation point, which is square root z square plus d by 2 square. And for other charge, it is also the same. So we have 2 beta. This is the potential. For field, you just need to take the gradient. You can see there is a variable z here, so that means this will be z cap dou by dou z v. You can cross check also. You can cross check the answer you are getting here and the answer we have got before to check whether it is giving the same expression. Dou by dou z, dou beta q root z square plus d by 2 minus z cube to beta q, and this will give minus of 2z divided by z square plus d square by 4 d by 2 in p cap direction, right? Okay, z cube is already written. This will cancel. So you have the electric field expression is 2 z 4 pi epsilon naught z square plus d by 2 whole square d by 2. So you can see it here how easier this one to find out the electric field. But for this, you need to know what is the potential to find out the electric field. Okay. So this is for the first case. For the second case, it's a continuous charge distribution of lambda. And I think the distance was same. You need to calculate the field here, the distance z, and the length here is 2a. Finding the potential is easy. You just need to take a small length element from the origin. Let us say this is dx. And because of the dx, you will see a potential. Can we directly find the field? Um, for this simple charge configuration, like here it is only a discrete point charge. So that is where you can easily find out the field here. But whenever you have a continuous charge distribution, then you need to see, you need to take the integration. Here also you need to see which one of which of the symmetry is cancelling with each other. Then you just add up the non-zero field component to find out the field. And I don't think there is any direct method of finding the filter because you can't use the Gauss law here. So I think no. You have to follow either the conventional method, that is, take the small area, small length element, find out the small field, then integrate it, or Gauss law whenever you have a symmetric charge distribution, and what else? Or the potential. But as you solve different types of problem, uh, you will be become more comfortable in finding the field even after using the first method because you know the steps. You can easily find out what is the symmetry or which component is cancelling. Then uh, you won't take that long to find out the electric field. Okay, so for the potential here, it is 1 by 4 pi epsilon naught lambda r prime dl prime dl prime r. So this is r here. This distance we are taking. The receiver P point is also here. So R will be square root x square plus z square. Lambda dl is dx square root R is x square plus z square. From limit minus L to L. So this distance is 2L. You can take 0 to L or you can take minus L to L. Whichever is, it will give the same result. For this, if you recall, you need to remember the steps to find out the integration because these are crucial. So this will take a significant amount of time if you don't know how to calculate. So 1 by square root x square plus z square, if you recall, this will be ln x plus square root x square plus z square. Just remember the formula, okay? Instead of finding the you using the steps, just recall 1 by square root of x square plus z square will give ln x plus square root x square plus z square. So this will save a lot amount of time. And the integration is from minus L to L. So what we now is, let us write beta and ln L plus square root L square plus z square minus L square root L square plus z square. This is the field, and for electric field, so that was the potential, and for electric field we need to take the gradient minus z cube lambda b dou by dou zeta v, which is ln L plus square root L square plus z square minus L square root L square plus z square. Ln x will give 1 by x. So let us solve it first. So ln a by b, you can recall it is ln a minus ln b. So I am taking the derivative of the first part. This will give 1 plus square root L square plus z square plus derivative of the top part. Let me write minus L square root L square plus Z square divided by Z minus L plus square root L square plus Z square. This will give Z cap lambda B. I think it's better if I write it in the next page. Mm. We'll give Z and L plus L square plus Z square. And there is Z square plus L square. I think we'll get a half X. Similarly, for the second, it's the same. Z minus L plus square root L square plus Z square plus L square. Just solve it, simplify it. I will get. I'm writing the final one. Lambda beta Z square plus L square minus 2 Z square plus L square minus X. We will get this. Okay. Solve it. We will get finally to lambda L by epsilon Z square root Z square plus L square Z. Okay. So this will be the field expression for the line charge density. Okay, so the question was, it was the second part of the 10th question. So there is a uniform line charge density of lambda and the length is 2L. So you need to find out the potential at the point P and the electric field at the point P. Okay, so Dinakar, is it okay if I move to next question, or you need some time to write question in detail? Okay. So for the second case, uh, so you have a finite line charge density. This distance is 2L, and there is a point at the midpoint of this line P. You need to find out the potential here and the electric field here. So for that, what we can do, we can take a distance x. Let us say there is a small length element And because of this small length element, there will be a potential at this point. P. This distance, I think it's given Z, and this will be R. Potential is a scalar quantity, so you don't need to worry about unit vector. So you just need to use the expression to find out the potential. Okay. So VR, if you recall, it will be 1 by 4 pi epsilon naught lambda dl and, the distance r, right? So we have now 1 by 4 pi epsilon naught lambda dl is dx, r is square root z square plus z square. And the integration is on x. X is varying from. So we've taken this point as a origin. So that is why we have taken the limit minus L to L. You can start from here also and take the limit from 0 to 2L. So now we have 1 by 4 pi epsilon naught. Lambda is a constant. Dx is square root z square plus z square from minus L to L. And for this integration, 1 by square root x square plus z square, what you need to remember what is the final expression for this integration, because it will take a lot of time if you find out the integration by taking the substitution. So it's better to remember the final formula here. So this will be ln x plus square root x square. You can assume x as tan theta. You can get the same expression. Okay. But in problem where which will take a longer time. So for that case, I think if you already know the formula for this, then you can save time also. So that is why I said to remember the formula. Only few of the formula you need to remember. You don't need to remember all the formula. Okay. So this will give ln x plus square root L square plus z square minus L plus square root L square plus z square. You know the potential now. Now you can easily use the gradient of the potential to find out the electric field. So minus zk dou by dou z v. Okay, let me know, Dinakar, whether I need to show the derivative or I can skip it. I think you already know how to calculate the derivative, and I have shown the steps before also. This beta you can take 1 by 4 pi epsilon naught. So this will be lambda beta zk dou by dou z of ln. Let's say this is a by b. Okay. So to just calculate the derivative and check whether the answer is matching with the answer I'm getting. Okay, so let us move to our next problem. Question says there is a uh, conical surface can. Uh, okay, So there is a conical surface. You can imagine it a empty ice cream cone. And this conical surface carries a uniform surface charge density sigma, and the height of the cone is h, and h is the radius of the top. So radius of the top and the height of the cone is h. And for this cone, you need to find out the potential difference between the points A, which is the vertex, and the point B, which is the center of the top. So let me draw the diagram first. So we have a cone and one empty cone, and this has surface charge distribution sigma. And it is given the radius of this top is h, and height of the cone is also h. You need to find out the potential at the vertex, which is the point here, and the center of the cone at the top, B. So the steps is same. You need to take a small charge element. So let us take a small charge element at a distance. Let us say this is R, and this has thickness dr. Will be a circular charge element. Let us say this radius, it is R, small r, and the distance from the top B to here is R prime. So we need to find the field at B, sorry, potential at A and potential at B. So that is why I have defined the distance R and R prime. So VR, it is beta sigma R prime D prime by capital R. So this is the general expression, and sigma R for this small area element, it will be sigma 2 pi R dr, right? And what else? Okay, distance. So this will be sigma R d, the total charge. And one thing you can notice, okay, let us first calculate the imputation. This will be beta sigma 2 pi R dr and R. You can see here we have two variables. One is smaller and one is curlier. So we need to express only in terms of one variable. For this, you can see the triangle. Let me take this. So you can see the triangle here. This triangle. From this triangle, you can, or you can also see the bigger triangle. You can see the radius of the top is, this is h. Also, this length element is h. So that means this angle will be 45 degree, right? This is 45 degree. And for the smaller triangle, you can easily relate R smaller and the curlier. So smaller and the curlier, it is, if you take sine 45, is R by del R. So that means R is, sine 45 is root 2. So we know the relation now. So just put it, VR is, so VR is beta, sigma is a constant, 2 pi, smaller is r by root 2, there is a curly area, dr. And what will be the integration limit? The integration limit will be on r, right? So r is varying from point A, which is at the 0, to a point here, because this covers the whole surface charge. So that is why this point, this length is root 2h, right? So that is why we take the integration 0 to root 2h. R will cancel. So we have now root 2 pi beta sigma integration of dr from 0 to root 2h. So, so this is at the point A, right? We are calculating at the point A what is the potential. This will give 2 pi beta sigma h or sigma h by 2 epsilon. This is at the vortex. Now we'll see what will be the potential at the center of this top. This, let me draw it again. So we've taken a small length element here, and from point B, this distance is r prime, this is dr, and this is r. This is A, B, capital R. This angle is 45. We've calculated it. So VB will be beta sigma 2 pi r dr and r prime. Instead of curly r, we have r prime. So beta sigma 2 pi r dr. So we need to express in terms of only one variable. So let's take, we want to express in terms of r now. So for this, what we can do, you can see here, this is r, this is r prime, and this is r prime. Okay, h, you can take this one. Because we know this angle, so that is why we try to use that angle to find out the relation between r and r prime. For the smaller one, it was easier, but for this triangle, we don't know the angle. So that is why we are following this steps. So for this, you can see r plus r prime. We want to find it here. R plus r prime is h, right? So that means r prime is h minus r. And what is the angle between HR? It is 45. So that is why this will give s square plus r square minus root 2 HR. Okay. So VB is 2 pi beta sigma r d r root h square plus r square minus root 2 HR. And r is r by root 2, small r is r by root 2. So you can put it here, r by root 2. And the integration is from 0 to 2. sigma 2 root 2 epsilon naught 0 to root 2h r dr. So to solve it, what is the trick that you can follow? You can say there is a r here and there is r square here. So that is why if you can somehow take it as x and it's some derivative of x, then you can easily find out the answer. So that is why what you can do. So r square derivative will give 2r. So that is why I can multiply 2 here. So we divide 2 here and multiply 2r here. Plus we can add root 2h plus root 2h so that the numerator doesn't change. dr by square root h square plus r square minus root 2h. Now it's easy to find out, right? I think you can easily guess what is the next step for you to follow. This is 4 root 2 epsilon naught 0 to root 2h. You can divide into two parts. One is 2r root 2h by square root plus root 2h by square plus r square minus root 2h of dr. This one is easy. This is dx by x. So you can take this h square plus r square minus root 2 hr is some x square. So this will give 2x dx is 2r minus root 2 dr. So that means for, let's say, for a part, the integration will give x by x. So 2 times dx. That is 2x. 2 x is square root h square r square minus root 2 from 0 to root 2. This is for the first part. For B part, you can see here this is root 2h is a constant. Root 2 is a constant, and there is some terms of h square plus r square minus root 2hr. But you can you can make it as a whole integration. Sorry, whole square, right? So if you add some constant and subtract some constant, you can make it as some constant square. So for this, what you can do, the second part will root 2h dr square root square plus r square minus root 2hr. This you can take h square r square root 2hr. This is 2r h by root 2 plus h by root 2 square minus h by root 2 square. So this will give r minus h by root 2 square plus h square by 2. So why I do it this way? Because if we recall, we know the integration of 1 divided by x square plus z. So you can directly use that formula to find out the integration value. Okay. You can take it, this is some x square, this is z square. So x I'm taking is r minus h by root 2, z is h by root 2. Now it's easy to find out. This is dr root h by root 2 square plus r minus h by root plus 2. This is root 2h dx by square root z square plus x square. The value is root 2h ln x plus square root x square plus z square. Its limit, so root 2h ln x is r minus h by root 2 plus square root square by 2. So now we know the integration limit. Just put the limit for A and for B. So BB will be sigma by 4 root 2 epsilon naught. Let us write the single expression first. And there is a limit 0 to root 2h. If you put the limit here, 0 and root 2h, this will give 2h minus 2h. This will cancel. And for the second part, it will give root 2h ln root 2h h by root 2 plus square by 2 root 2h minus h by root 2 square minus root 2h ln for 0 it will be solve it. Just simplify the terms. You will get, let me write the final. Finally, you will get sigma by 2 epsilon naught h ln 1 plus root 2. Okay. So now we know VA and VB. So VA minus VB will give, this is sigma by 2 epsilon naught. Other one is sigma h by 2 epsilon naught ln 1 plus root, which is sigma h by 2 epsilon naught 1 minus ln 1 plus root. Okay. So this is how you can calculate the potential for a pole. Okay, so is the problem is clear to you? Do you have any doubt in any of the steps? This is the final answer you will get. Okay. So if it is, then the next problem is, it's a easier one. Electric field is given. Uh, and you need to find out what is the charge density and charge density enclosed by a cylinder of height h and radius r, and base, which is based on the xy plane. So the solution is easy. You just need to follow the differential form of Gauss. So if you follow that, you can easily find out what is the charge density and the other cases. Okay. So I'm skipping this. We'll try to calculate it first if you have any problem. I don't think you will have any problem. So if you have any problem, then I will cover this one in the next lab session. 13 also, it will take some time. It is similar to what we have seen in one of our problem. So if you recall, we have seen one problem when there is a large conducting plate and there is a hole in it. So for this one, there is a sphere and there is a cavity inside the sphere, and you need to calculate the electric field and the potential. We'll see it in our next live session. Okay, for now, let us stop here. So we have covered mostly the potential and the one question on potential energy. I think two question on potential energy. In next live session, we'll try to cover more on what is dipoles and more problems on electrostatic potential energy. Okay, so I hope the problems that I've solved will be useful for you to solve the assignment, and the solution of this problem is clear to you. If not, feel free to ask me the problem anytime, either in the discussion forum or in the live session. So we'll meet on next Friday, same time from 6 to 8. Try to join the live session. It will be helpful for you. Okay. Okay. So do you have any doubt? If not, we'll stop for now. Okay. So if it is clear, then let us end our live session here. Thank you for joining the session. Let us meet on next Friday from 6 to 8. So bye everyone.